All right, so we talked about type 1 error, which the probability of that occurring is the alpha level. Type 2, where the probability of that occurring is beta, power, effect size, all these things. And actually, the beta, alpha, and power kind of work together or against each other in different ways. So if we thought that a type 2 error would be really bad, we could reduce beta for all of the alternative parameter values by increasing alpha. So those two work opposingly, okay? That means that reducing beta increases the chance of a type 1 error, since it would increase alpha. So this tension between type 1 and type 2 error is inevitable. The only way to reduce both types of error is to increase the sample size. Okay, so below here I have a little picture to help show what's happening here. So this top normal model would be the normal model we would get if the null hypothesis was true. Okay, this where, you can see that it's centered at P naught. Now, if the null hypothesis is not true, the normal model would not be centered at P naught, and it would be centered around some other P, like in this bottom normal model. Okay. Remember, we don't know whether the null hypothesis is true or not. So we might be on that top normal model, we might be on the bottom, we're not really sure, okay? So I'm gonna take this line right here, I'm making it pink so you can see it, and if I want to decrease the chance of a type 1 error, I would wanna make alpha smaller. But notice how the area where beta is would get bigger. So decreasing alpha increases beta. If I go the other way and I say a type 2 error is bad, let me decrease the chance of a type 2 error. Oh, now it's increasing the chances of a type 1 error. It's increasing alpha. And notice that when I increase alpha, so here I am increasing alpha, the power gets larger, right? It's going to be more likely that I correctly reject a false null hypothesis if the chance of rejecting is higher, okay? If I increase beta, the power gets smaller. So it's important that you understand how these things play into each other, okay? So reducing beta will increase alpha and increase the power. Reducing alpha will increase beta and decrease the power. So alpha and beta work hand in hand. Alpha and power work hand in hand. Alpha and beta are kind of opposing. All right? But if we increase the sample size, if you turn to the next page, you can see that those darker colored ones, those are the increased sample size, right? We know from the central limit theorem that if we have a larger sample size, our spread is going to be smaller. So if your spread is smaller, then you have less chance of overlap and therefore less chance of making either error. Okay, so that's just another picture to show you what's happening. Increasing the sample size is going to reduce both types, the chance of both types of error. Okay? Now, let's go through an example where we kind of talk about type 1 and type 2 error in context. So testing for Alzheimer's disease can be a long and expensive process consisting of lengthy tests and medical diagnosis. Recently, a group of researchers devised a 7-minute test to serve as a quick screen for the disease for use in the general population of senior citizens. A patient who tested positive would then go through the more expensive battery of tests and medical diagnosis. The authors report a false positive rate of 4% and a false negative rate of 8%. Put this in the context of a hypothesis test. What are the null and alternative hypotheses? Okay, so we're not going to use P here. We're just talking about you are a doctor. A senior walks into your office. What are you going to start out by assuming? you would assume that the person is healthy until you found evidence otherwise, right? Person is healthy, meaning they don't have Alzheimer's. You're not just saying to every single patient that walks in, I think you have Alzheimer's. Let's prove that you don't. No, that's not how that works. Okay? So your alternative, if they're not healthy, for this test in particular, then we're going to say they have Alzheimer's. So, what does a type 1 error mean in this context? Type 1 error, remember, that means that the null hypothesis is true, but we reject it. So, that means the patient doesn't have Alzheimer's. Oh. Yeah. The null hypothesis says the person is healthy, so the patient doesn't have Alzheimer's. But our test says they do. Okay? So the null hypothesis is true. They don't have Alzheimer's. But we reject it, meaning they took the test and we said, we think you have Alzheimer's. Okay? Type 2 error. Remember, that's a 2 F's. Null hypothesis is false, but we fail to reject. So, if the null hypothesis is false, the patient has Alzheimer's. But our test says they don't. Okay? The null hypothesis is false, but we fail to reject it. Now, which is worse? Would it be worse to have a type 1 error here or a type 2? And this is your personal opinion. No one is going to keep you to whatever you say on the AP exam, right? If you say, I think a type 1 error is worse, no one's going to hold it against you for the rest of your life, okay? You have to pick a stance and stick with it. Do not say both are bad. That's not answering the question. It says which one is worse. So let's think about it. If we have a type 1 error, that means that the patient didn't have Alzheimer's. We did that first test. It came back positive. They go through all the other tests. Okay? So maybe along the lines, it says that they don't have Alzheimer's, they figure it out, but now they've paid for all those testing things, they've gone through, maybe taken some medication along the way, they've been stressed about it. Those are some negatives of type 1 error. Type 2 error, the patient has Alzheimer's, but the test comes back negative, right? It says they don't. Well, now they're not getting the treatment that they need. Okay, so which scenario do you think is worse? I'm going to go with type 2. If you disagree, feel free to write your sentence for type 1. So I'm going to say a type 2 error is worse because, and notice I picked one. I'm not waffling, I'm picking one. Because it would mean that the patient will go undiagnosed and not get the treatment that they need. And then I'm going to talk about how a type 1 error isn't that bad. A type 1 error would just mean going through more tests and would hopefully end in a proper diagnosis. Now, what is the power of this test? Well, we know that to calculate power, we can find that by 1 minus beta. In this problem, they actually tell us what beta is. Remember, beta is the probability of a type 2 error, meaning the patient has Alzheimer's, but the test says they don't. That would be a false negative. So this is telling us that beta is 0.08. Now, if we think a type 2 error is bad, we would probably want to reduce the chance of a type 2 error. So maybe we end up with a higher alpha level, right, to reduce that beta. That's how you can kind of choose back and forth between, oh, is type 1 worse or type 2? Should I have a higher alpha or a lower alpha? And that's what you're deciding when you do your hypothesis tests, okay? So if beta is 0.08, then the power is 0.92. So what does that mean? I'm going to say the power is 92%. This means there is a 92% chance, what is power? Correctly rejecting a false null hypothesis. That the test correctly identifies patients with Alzheimer's. And power, that's what we want to show. We want our test to diagnose people with Alzheimer's, and we want it to be right. That's the real goal here. So power is typically what you want to show and actually being able to show it and it being correct. That's what you want. All right, that's the end of chapter 20. You're now free to do any questions on the homeworks that you want. If you have any questions, feel free to go on AP Classroom and look at those videos or send me an email after you've done that.